Sir, we are live, sir. Please start.
Okay, thank you. Okay, we'll solve a couple of more problems for the week 3. So your assignment is due this week. So we'll solve some example problems which will help you to solve the assignment. Okay. Okay, so it's about power and energy. This assignment is meant for. So let's try to determine the power delivered by the current source in the figure below. So we want to calculate the total power delivered by the source, right? For that, we need to know the total resistance. So now if you see, looking here, what is the total resistance? This is 3 kilo ohm, that is 2 kilo ohm, that's 5 kilo ohm. So 5 kilo ohm is in parallel with 1 kilo ohm. So the equivalent resistance R equivalent is 1K multiplied by 5K divided by 6 kilo ohms. So that's an equivalent resistance. Now, the source is always going to give a power only, right? But it's pushing current in this direction, right? So now, if you calculate this power is basically equal to I square times R. So what is an I? I is equal to 12 milli times 12 milli multiplied by the R is 5K divided by 6, that is 2. So this milli K goes, so 5 to the 10, so 120 milliwatts is the power given by this current source to the network. Easy question. And the second question is, in the figure below, in the circuit of the left, the network in which consists of only of resistors draws an energy of 1.2 joules over a period of 1 minute. The same circuit is driven by 20 volt source in B. Determine the current I1. So the network is same on the left side and the right side. Now we wanted to find what is the value of I1. That's our target. Okay. Now let's try to solve this here. Okay. First is, we have taken 1.2 joules in 1 minute and the source is 8 volts, correct? So now, if you know power is defined as voltage into current. Power is equal to voltage into current. Now the voltage applied is 8 volts and the current we do not know, right? We don't know the network, but we know that the energy in the network is 1.2 joules. So the energy is defined as power multiplied by the time t. So the energy given as is 1.2 joules and the power is 8 times I times t. And the time is given as how many minutes? 1 minute, which is 60 seconds. 1.2 joules, 8I times 60. So this I is basically is equal to 1.2 divided by 8 into 60. This much is the current taken by this network. So why are we interested in that current? Because we wanted to find equivalent resistance there. So the R equivalent, looking here into this network, we are interested. So R equivalent is given by the applied voltage divided by 1.2 by 8 by 60. So from this, you can calculate the equivalent resistance. Or you can also do another simple trick here. The voltage here, since the network is not changed, The current I, see the current I is pushed in the same direction here, and here I is entering and I is leaving. So this is, if this for 8 volts, if it's giving this much current, this is for 8 volts. If 8 volts becomes 20 volts, the current I1 also increases by same factor. So I1 becomes 20 by 8 times 1.2 divided by 8 by 60. This way also you can solve. Either you can find the resistance from this data, current from this data, from there you find the resistance. If you know the resistance, then you can also calculate the R equivalent as simply 20 volts if you apply divided by the the current I1 you can calculate by 20 volts you apply divided by equivalent resistance you got. Like this you can compute. Okay. Okay. Now let's try to solve the next question. Now we have an inductor here. We wanted to determine the energy delivered by the voltage source from t equal 0 to 3 microseconds in the figure below. The inductor current is 0 at t equal to 0. So initially there is no current in the inductor. Now the current in the inductor has gone like a triangle and went back below. So we are interested to find at 3 microseconds what is the current. What is the energy given by the source? Now here there are two things here. There is a voltage source. There is also a current source. So we are interested in power delivered by the voltage source. Okay, energy delivered by the voltage source. Now we know very well that if you keep the voltage across the inductor constant, so voltage across the inductor constant, so we know that the voltage across the inductor and the current through it are related to E equal to L di by dt. Right? Now, similarly, the current if you want to find, which is 1 by L integral dt. Right? So either way you can find. So this is the current through the inductor. This is a voltage. Voltage and current are related to these relationships. Okay. Now I would like to compute this current through the inductor and find the energy delivered by it. Now, the question here is, already the current source is giving some current, the profile is given, right? And so there is no problem. So first what we have to do is we have to find the current which is going into the inductor, right? If we know the current which is going into the inductor, then we can find the energy delivered by the voltage source also accordingly. Okay. So if we see the current in the inductor 1 by L integral, there is no initial current in the inductor, so it's basically 0 to t. So voltage across the inductor multiplied by dt. Okay, so this is 1 by 2 microhenry integral. We are interested from 0 to 3 microseconds, and the voltage across the inductor is constant 5 times dt. So basically, if you see the current in the inductor is 5 by 2 times t. Right? So that is 2.5 t. So that's what the current in the inductor is. Right? Now we are interested in how much of this current. So this is the current which is going to the inductor, but that's part of that current also can be given by the current source. Now we need to find some of the power can come from the voltage source, some of the power or energy can come from the current source, right? So this is the profile of a current which is going through the inductor. So this is T. This is the current in the inductor IL, so it is going here. If you see, it's a linear function of time, 0, it's going with 2.5 slope. Okay, now what is the power or energy given by the inductor? So voltage source we are interested. So let's try to figure out what is the current which is given by this 5 volt source. Let's call it as I5, right? Now I5 is basically equal to, so there are, if you write a KCL here, let's call this as I1. Now I5 is entering the node, I1 is entering the node, and IL is leaving the node, right? So what is I phi, which is IL minus I1? Okay, so we know IL, we know I1, we have to subtract it. Then we have to integrate that current, correct? Okay, now if you see here, and we have to integrate it, right? So we are interested in first power given by 5 volt source. Power is given by voltage into current. If I want to find the energy, I have to integrate it over the period. So 0 to t v times I into dt, where t is 3 microseconds. So 0 to 3 microseconds. What is the voltage? The voltage is constant here. And I have the current. The current is given by IL minus I1 into dt. So it means it's basically 5 multiplied by integral 0 to 3 microseconds IL dt minus integral 0 to 3 microsecond I1 dt. So I have to integrate this guy and this guy. It means I basically need to find the area under those curves till 3 microseconds. Correct? Okay. Now for this guy, IL, if I want to find the area, right, till 3 microseconds, it is off. The base will be 3 microseconds. So the height will be 2.5 times 3 microseconds because the graph which describes it is 2.5 t. So it's basically 4.5 divided by 2 micro, that will be pico. That's an area. 1.2, 2.5 t. So this is an area because of the inductor current, which is 4.5 by t minus. Now let's try to find the area under this. If you see 1 to 2, whatever area I have got from 1 to 2, right? If I see here the area, if you see, that area is equal to 2 to 3. This guy went from 1 to 2 low, this guy went from 2 to 3 low. Now, what am I left is just with one triangle here. That triangle is off. The base is 1 micro and the height is 2 amps. So that gives me 1 micro here. Let me just see whether I made a mistake in this calculation. In this 0 to 3 micro IL dt. Yeah, I made a mistake here. So only 1 micro is there. Okay, so this becomes micro only. So this 4.5 by 2 micro minus 1 microjoule, whatever is that is. That is 2.25 minus 1, that is 1.25 microjoules. So I did nothing. I tried with the help of this voltage. I found the current in IL. If I know the current in IL, this is the equation. Now I want to find power energy given by 5 volt source. To know, I need to know the power first. Power is given by voltage into current. If I want to find the energy, I have to integrate it from 0 to t. So this way, I can actually compute my energy, right? It's very simple. So 5 times IL minus I1, because I wrote a KCL on that node. So 0 to 3 microseconds IL minus 0 to 3 microseconds I1. So you find the areas and you subtract it. Okay. Now we wanted to determine the power delivered by the 6 volts voltage source in the figure below. Okay. We wanted to find the power delivered by 6 volts voltage source. Right. Now, first we have to see how much current this fellow is giving. Right. For that, we need to apply a KCL. Okay. So if you see here, this is minus 7 amps. That is minus 9 amps. Minus 11 amps. If you see here, this is minus 7. This is minus 11. So the current in this branch should be minus 18 amps. I've just applied a KCL here. minus 7 coming here, minus 11 is coming. Sum of these two nodes should be equal to minus 18 amps. Okay. Now, this is minus 9, this is plus 10. So this is entering. So entering the current here is also minus 10. So this has to be minus 10 plus 9, minus 19 amps. Minus 10, minus 9, sum is minus 19 amps. So minus 19 here, minus 18 here, that's the current which is entering here, which is 19 plus 18, that's 37 amps. So the current which is going here is, the current is given by this fellow is 6 volts source is 6 times minus 37 amps. So it means actually this guy is taking the current, it's not giving the current. So power delivered by it is negative. So you can multiply it and write the answer. Okay. In the figure below, determine the power delivered by the 4 milliamp current source. Okay. Now, if you see here, this current source is giving a current based on that the voltage here is defined. Correct? Okay. So we want to find the voltage across it. What is the voltage across this guy? Is 2 kilo ohms times Ix. What is Ix? 4 milliamps. Right? So basically, if you see the voltage across the power source, which is 4 times 2, 8 volts. So it's basically the 8 volts is across this device like this. Okay. Now the question here is it taking the current or is it giving the current? That's what we are interested, right? Now the point here is, if I have a current source, if I'm pushing into some circuit this current source, then I should get a plus drop and minus drop here. That's a voltage, that's an I. So the power given by the source, the I source, is defined as V into I. Now in this case, if you see, if I rewrite this circuit like this, what do I get is, I get 4 milliamps, and there is an element here. That element can be anything, but I know that the voltage across it is this minus this plus, right? So it means the power delivered by this also is negative, which is minus 32 milliamp. Because if this guy is giving a current, it should have given a plus minus here. But if this is minus, this is plus, means actually the network is providing current back to the source like this in this direction. Okay, because of that, we can say that it's not delivering the power, it's absorbing the power. So the delivering power is minus 32 milliwatt. Let's see the next question. In the figure below, determine the energy delivered by the current source from t equal to 0 to 4 milliseconds. Okay, so we are interested in determining the energy delivered by the current source. This is the current source. The profile of the current source is given. Okay, so we are interested in, the answer must be in microjoules. Okay, we are interested in energy delivered by the current source. So to know that, we need to know the voltage across the voltage source. The voltage across the voltage source we want to find, let's say that is Vk. So minus Vk plus Vx minus Vx is equal to 0. So it means the Vk is equal to 0. It means the voltage across the current source is 0. So it means the answer has to be 0. Because there is no voltage across it. So you can say that the current is given by it is 1 second. So yeah, Vk is 0 means So it means it's simply this. Because those two are getting added up and becoming 0. It means the power has to be a lot of power it has to give, because it's a short circuit. You put a short circuit, it has to be infinite. Okay. In the figure below, identify the elements that are passive. Right? What is a passive element? Passive element means if you push current across it, it basically absorbs the power. If it absorbs the power, the voltage to the current ratio has to be linear, and it has to be so basically V by I ratio has to be positive. Correct? So it's a passive element. Now let's see that. Is it passive? Now if it's a passive, if you see here, the voltage is positive, but the current is negative. What does it mean? If I apply a positive voltage across it, instead of taking current, it's giving current. So it cannot be positive, passive. Now, this can be passive because the voltage and current are proportional, and for a positive voltage, you got a positive current. Similarly here, this cannot be passive. Similarly here, a passive element, if you apply 0 volts, right, then okay, let's look at this again. D is passive or not? We have to check it. Okay, let's come back to D later. So H is a passive element and E is a passive element because the voltage and current, if you see really, okay, I'll clarify this question in the next week. Don't worry about it. Okay. Determine the power delivered by the -5 volt source in the figure below. Okay, so we wanted to find the power delivered by this guy. So we want to know the power delivered, we need to know the current also. Okay, how do I figure out the current? Is a question here. Okay, there are multiple ways to do it. I'm just thinking what is the easiest way to solve this network. Okay, this is R, this is 2R, this is R, this is 2R, this is R, this is 2R, this is 2R. This is a network we have. Okay, now okay, you can write a KVL around this loop. If I do that, so this is -5. Actually, it means this is plus, this is minus, this is plus, and it is +5. So +5. The current in the resistor here is, let's say, I1 +5 plus I1 times 5K. And I do not know the current in this, right? Let's call it as some I2, then that is the current in this guy is I2 times 2R, which is 10K, plus 5 is equal to 0. So this minus 5 plus up top bottom. So I replaced it like this. So plus 5 plus I1 into 5K plus I2 into 10K plus 5 equal to 0. But in this equation, we have two unknowns and one equation. Now let's try to set another equation to solve for the I2. Okay, I do not know how to solve for the I2. So let me call this as this current which is going here in this branch of 5K is I1 minus I2. Right? And if that is I1 minus I2, and what would be the current here? So I want to write another loop here, right? I can make any loop around, right? So I'm going to write a KVL. I'm going to make a KVL around this loop. Okay, so minus 5 plus I1 minus I2 times 5 kilo ohms, right? And I don't know the voltage across that guy, right? So since I do not know voltage across that guy, so if the current coming here is I1 minus I2, and what is the current going in this branch, I have to figure out, right? Let's call that as some I3, which I don't know, right? So plus I3 times 10K is equal to 0. Now, if you see here, I have two equations and three unknowns. It means I am forced to make another equation, right? So that equation can be again, this is the current is going like this, so plus minus. So minus I3 times 10K. So I'm writing a loop from in this direction. Okay. Plus, now the current which is going here is I3. The current coming is I1 minus I2. So I1 minus I2 minus I3 minus 5 milliamps multiplied by 5K, right? Okay. Plus, and I do not know the current which is going into this 2R, let's call it as an I4, is equal to I4 times 10K plus 20 is equal to 0. Now I have a 3 unknowns and 4 unknowns and 3 equations. So what I can do is I can write another equation here. I can write another equation in this and figure it out. So what is this final equation is? Minus 20 minus, so I3 is entering like this, so this is plus, this is minus, I3 times 20K plus, so this is an I3, and just a second, yeah, that's an I4 times 20K. So if this is an I4, then the current which is entering here in this branch is I1 minus I2 minus I3 minus 5 milli. So I1 minus I2 minus I3 minus 5 milli multiplied by 10K is equal to 0. So basically you have 4 unknowns and 4 equations. You can solve them and figure out the I1. Once you know the I1, now the source is given like this, plus minus I1, right? And this is minus 5 volts. So now basically, if the element is giving the power, then from the plus, it has to give a current. It's delivering the power. So basically, you have to make it 5 and you have to find the current which is minus I1. So the power delivered by 5 volts, minus 5 volts source is fundamentally 5 multiplied by minus I1. Whatever answer you get, you can write it. Okay. Now I think this you can solve at home. This also. This is just a formula based thing. Okay. So this completes. I'll post these notes to you. You have any doubts in these questions? Whatever we discussed, you can ask. See, a voltage source and current source can either absorb the power, can give the power. It depends upon how you are using it. For example, if this is a voltage source and the current which is coming out of this voltage source happens to be I, and actually it's delivering the power. So what is the power delivered by this voltage times I? But if found that the I is negative, it means it's absorbing the power. This is the point you have to remember. Okay, there are no questions. Okay, thank you. So I'll post these notes in the classroom. You can go through it and you can ask the questions if you have any doubts. So I'm ending the class here.